let's get started with pooling rules in design of experiments. So let's get started. This is being brought to you by educatevirtually.com. Alright, so pooling rules, and we'll go through an example so you can understand a little bit about this. But the first pooling rule is to remove factors from your model that have an F statistic that is less than or equal to 1. Alright, that's the first rule. Now, why would this F statistic, less than or equal to 1, mean anything, make any difference? Why do we even care? Well, the F statistic is equal to the mean square for a factor divided by the mean square for the error term or the unexplained term. So if this value is going to be less than or equal to 1, it means that the unexplained term is bigger than the factor. And we're not going to bet any money on the unexplained term. So if it is larger than the mean square for the factor, it's no more significant or important than the unexplained. So we remove it from the model. Alright, the second pooling rule is then you remove the next smallest factors from the model based on the F statistics until you get to about half of all of the variables that you started with in your designed experiment. And that would include even if you had some dummy columns in your model. Alright, so let's take a look at an example so you can understand how Rule 1 and Rule 2 can be applied as you reduce the number of variables in your design, because we want to separate the vital few from the trivial many. So just because you put it in the design experiment doesn't mean that it's going to be significant. So let's take a look at an example here of a experiment, and we'll start with an experiment layout. Now this is a Yates algorithm. It has 16 runs. I can study up to 10 factors and up to 5 combined effects or interactions, and you can only choose one from each of these groups to make sure that the combination of pluses and minuses that you would have in the interaction is not the same as the combination of pluses and minuses that you would have for the main effects. Alright, so we're going to use this model. The example that we have is a machining experiment, and in this particular experiment we have factors of speed, feed, depth of cut. We also have the coolant quantity, the coolant cost, different types of tooling, and then we have the combined effects of speed and feed. Okay, so speed times feed. We have speed times depth of cut, and we also have feed times depth of cut. Now, to get at these patterns of pluses and minuses, if we were to go back to our layout, what we did was we actually multiplied the columns together, and a minus times a minus would be a plus times a minus would be a minus times a plus would be a plus times a plus is a plus. So that's how we get those. And we also have a situation where we didn't use all 10 of these, so we assigned what we're calling as these are just unused columns. So we call them U1, 2, 3, and 4. Now we don't expect that there should be anything significant happening with these because there's no variable there. If something does show up in these, then we have a major problem in our experiment. But we'd expect that these are not going to turn out to be significant. They shouldn't be because there's nothing there. And But we are going to try to find out, does speed, does feed, does depth of cut, do the combined effects of these variables make a difference? Our coolant quantity, our coolant cost, our type of tooling. And what we're trying to do is minimize the cost per pound of material removed. All right, so this is actually the result of setting up this experimental combination here, and that was the cost per pound of material removed. We ran this particular combination, here's the cost, etc. So let's take a look at the first initial analysis of variance. All right, so here we have all of our sources. All right, each of these has two level settings, so there's 1 degree of freedom. We have our sum of squares. We divide our sum of squares, okay, and by the degrees of freedom to get our mean square. And then to get the F statistic, we take our mean square and we divide it by the mean square for the unexplained term. So here's our unexplained term here. There is the mean square for the unexplained or the error term. And then we get these F statistics that are calculated. Now right now I'm really not going to look at these p-values because until we've reduced the number of factors in our experiment, they don't really make any, they're not significant from the standpoint of this error term has not been pooled. Now what happens is as we begin to take factors out, we are going to increase the sum of squares. We're also going to increase the degrees of freedom. So in essence what's going to happen is this mean square for the unexplained is actually going to get smaller. All right, so let's look at the first factors, and we can see that we have a value of 1. We have a value of 0. We have another value of 0. All right, and then we take the next smallest ones. Now in this case we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 divided by 2 is somewhere around 6, approximately 6 to maybe 7. All right. So that's about how many variables that we should have left after we've reduced the number of columns from our experiment. All right, so now we're going to take the next smallest ones. All right, so we've got 3.53, 3.69, and the next smallest one is going to be 18.16. And where are we at now? We've got 1, 2, 3, 4, 5, 6, 7 factors left. This 24 that we're looking at here, it's actually the tool itself, and it doesn't really look like that's going to make a difference at all. So we're going to take it out of the model. So you can see that we've got some really big F statistics and some pretty good sized ones. And we've taken all the smallest ones out. And now all of their sum of squares is going to get pooled into the error term. Their degrees of freedom will be pooled into the error term. We'll calculate a new mean square, which is just the sum of squares divided by the degrees of freedom, and that's how you get your mean square. And then once we get the new error term mean square, we'll recalculate our F statistics for the factors that remain in the model. All right, so now we can take a look at that from the standpoint of here is the final analysis of variance, and you can see now here's our F statistics, and our p-values, okay, are now telling us that we've got some very significant factors, and we know that 1 minus p gives us our confidence. And if we see that 1 minus something that's really, really small, 0.000 some number, all right, that's giving us some 99.99% confidence that there is a difference when we change the level settings for these different factors. So that's how we reduce the number of factors that we started from down to the ones that are significant. All right, and another way to take a look at this, and we'll just quickly take a look at it with a ANOVA table. Here we have an ANOVA spreadsheet that allows us to take a look at the F ratios and then decide which ones we're going to pool. All right, so we've decided which ones we're going to pool. We're going to go to the second part of that spreadsheet. All right, and now we're getting this really cool thing called pure sum of squares and percent contribution, and these are things from the good Dr. Junichi Taguchi. And one thing that's important is to look at is, what is this unexplained percent contribution? So if this is something that's much, much less than 50%, we can say that yes, we've got a really good experiment. And now we can take a look at, we can say we've got speed at 12%, feed at 51%, depth of cut 23%. So this is the amount of the variation that was explained when these factors changed between level settings. And we can also see that the speed times feed and the feed times the depth of cut were significant combined effects. So it's really an additive. All right, so if we want to look at the feed and the depth of cut, all right, so we've got feed, we've got depth of cut, we've got this combined effect. It's really 51 plus 23 plus the 4.48, and that gives you an estimate of the percent of the variation that's explained by this significant combined effect. All right, so that's how we take a look at the pooling rules, all right, from the standpoint of pooling rules and design of experiments, brought to you by Educate Virtually. And take a quick review of the pooling rules. First pooling rule is to remove any of the factors at F statistics that are less than or equal to 1. Next, you remove the next smallest F statistics until you've got about half of the variables that you started with in your experiment, and then you can make your final ANOVA table. Once you've done that, then you can actually plot your factors out. And in this case, we're trying to minimize our cost per pound of material removed. So we can see that we want a speed of 150. Here's our depth of cut and our feed, our coolant quantity, and we have our significant combined effects, where we have our speed at 150, our feed rate at 0.025, which is where we want to be. We have our depth of cut at 0.65 with a 0.025 feed rate, and that's right there. So that's how we finalize, and now we actually would go out and set this condition and see if we can meet our prediction. And that's all brought to you by EducateVirtually.com, and we do have Basic Design of Experiments training and Advanced Design of Experiments training at EducateVirtually.com.